Okay, so now we want to introduce the idea of voltage. All right, what is voltage? So to introduce voltage, we're going to need a couple of concepts. First, we're going to reintroduce the electric field, or at least talk about the electric field. And we're also going to talk a little bit about the concept of potential energy. And don't worry if you haven't had the previous physics course where potential energy was introduced. We just need a few basic things from it, all right? We just need a couple of basic ideas from it. And this will give us everything we need to introduce the idea of voltage, all right? So let's talk about potential energy for a second. And there are several different types of potential energy, but the first one, and really the only one we need to talk about, is that of gravitational potential energy. So imagine that I have a box, all right, and it's just sitting on the ground. And of course we know that a box or a block or whatever is just going to sit there. But what if I attach a string to it and I raise the box up? So now my box has been raised some height. I know what my height is, right? And what will happen? Well, we know what's going to happen. I have to keep holding the box with my string or some mechanism, or else the box is going to fall back to the ground and splat, right? The box is going to hit the ground and something will happen to the box, whether it will break or the contents in the box will shatter or scatter or whatever. That's all dependent on the particulars, but that's not important. The idea is that something happened as the box was falling, and as the box was falling it was losing this potential energy. Okay, so as the box falls, it lost potential energy. All right. So as the box fell, it lost this potential energy that it had. So in a nutshell, potential energy is the stored energy in a system. So as I was holding my box above the ground, okay, there's stored energy here. The energy isn't going anywhere or doing anything, it's just sitting there. Only after it starts falling does that energy start to get released. Right? So only as it's falling is E released. All right? So essentially what this means is that I had to work against the gravitational force, right? As I pulled the box up here, I had to work against the gravitational force. So to pull the box up, I did work against the gravitational force. Right? I did work against the gravitational force. And we can also see this because near the surface of the Earth, right, gravity also has field lines, much like an electric field, and near the surface of the Earth, where we can ignore the curvature of the Earth, these field lines point straight down, right? So the natural state of the box is to follow these field lines once I let it go, right? Well, we have the exact same situation in electrostatics, right? So imagine that I have two plates, right? And on the first plate, the top plate, I have all sorts of positive charge. These are conducting plates, right? So metal plates and whatever. And I have all sorts of positive charge on them. And on the bottom plate, I have negative charge. Well, we know that electric field lines will start on the positive charges and terminate on the negative charges. So my electric field is going to look something like this. And particularly away from the edges, right, this field will be more or less uniform. So over here, the gravitational field, the gravitational field is approximately uniform, and over here, the electric field is approximately uniform in the central regions. Right? So in here we have a uniform electric field. Alright, so how can we talk about this to introduce the idea of voltage? Right? So the entire idea here is, let's do this on a bit bigger scale here. The idea is that I have, again, two plates, and on the first plate I have lots of positive charge, and on the bottom plate I also have some negative charge. And so again, my electric field lines are going to look like this. Alright, and we don't need to worry about what the edges look like. Right, so the electric field lines over here are going to be bowed out a little bit, and they're not going to be completely uniform. But that's not important. We're only looking at the central region here. So imagine that I have a particle here that has some positive charge on it. It could be whatever. It could be a single proton. It could be an object with a lot of protons on it. As long as the charge here, the positive charge on the particle, is much less than the charge on the positive plate. All right. So these field lines act much like the gravitational field lines. If I want to lift this particle up, I have to attach a string to it and lift him up. I have to pull him up against the electric field. And when I do so, he'll no longer be at the bottom of the plate. He will be up here, and now he will have some potential energy attached with him, right? He'll have some potential energy. And that's because I've done work against the field. So I've done work against the field. All right. So I've done work against the field. Well, how much work have I done? All right. So remember that the definition of work, right? Work is force times distance. All right? Force times distance. So if we come back here, right? Remember that this field has a field strength of E, and this particle has a charge of Q, and the force that would be pulling the particle down would then be equal to F equals QE, right? We've seen that before. And so what this means is that the work I've done, if I lift it this entire distance d, all right, then the work done is going to be QED. All right, QED. That's the work done against the electric field. All right, and this is also the change in positive potential energy. All right, so this delta sign means change in. So change in potential energy. It's my positive change in potential energy. All right. And so what this means is that if I were to let this guy go, he would then, of course, fall back down this way toward the plate, and he would come to a resting spot on the plate, and he would then have no potential energy left. And so if he falls, that would be a negative change in potential energy. So if he falls, he experiences a negative change in potential energy. All right? And he happens to experience the change in potential energy that the magnitudes of these are the same, but he would experience negative QED, change in potential energy. All right. Okay, so that is the potential energy of an object in an electric field, would just be QED. All right. But we define voltage as the change in potential energy per the unit charge that was on the particle that we were looking at. So recall that this is QED divided by Q. My Q's cancel out because those are the same Q's. And so the voltage for a parallel plate capacitor is simply denoted as ED. And this is constant and does not depend on the charge of the particles in the field. All right, so the voltage doesn't change. That's why your outlet, the voltage is simply 120 volts, and it doesn't change no matter what type of object you plug into it. Right? So the voltage or the potential difference, sometimes this is called potential difference, of an object is completely constant. All right. So your batteries that put out 1.5 volts, that voltage doesn't change. Now, of course, for batteries, the voltage will change over time as the processes, the chemical processes in the battery are used up. Its voltage can drop, and it will be able to it won't be able to push out quite as much current. But that is essentially what voltage is. All right. So the next video will be just a couple of examples of how to use these kinds of ideas and the calculations that we can do with them. All right, we'll see you next time.